Today we're going to start a new topic called torsion, and this is one of those topics where I struggle to draw good pictures, so I have borrowed the pictures from our textbook. If I have a long, slender shaft, remember most of the things we deal with in this semester are long and slender because a lot of the assumptions we use work well for things that are long and slender. So long, slender bar is circular, and if you go around and you draw circles on it and lines, and then you apply a torque. So the torques here are represented by these little blue curves. We're applying a pair of equal and opposite torques or torsional moments. What's going to happen is that these straight lines that were down the length become a little bit skewed, twisted, but the circles we're going to assume are going to remain circular. Today we are going to talk about stress. And so the idea is that if you imagined your torque going around the circle like that, I'm going to draw a quick 2D picture to go along with this. If we have a circular shaft, we have a torque in this direction. They're showing you that a torque in that direction, if you use your right hand, would have your thumb coming out. So the torque vector is pointed in this direction. We're going to define that as positive internal torque. And if you took that and you cut it open and you zoomed in somewhere, what's going to happen is as you work your way around this circle, you're going to end up with an induced shear stress. Basically, this overall torque has got to be spread out all over this surface somehow. And so the way I like to think of it is imagine that a way to get torque would be to apply a whole bunch of little tiny loads that go all the way around the outer circumference of the circle. And that can help you figure out the direction of the shear stress. Direction of shear stress is something that tends to be kind of difficult for students with torsion problems. So this is just the cut open face. The shaft itself is actually a three-dimensional structure. So what we're going to be doing are drawing little volume elements, or I will call them little boxes, that look like that in 3D. So the idea is, let me draw a really big version of that little box in 3D when you're going to be asked to draw these in your homework. On the front surface of this 3D box, if it's coming from this location on the surface, is going to have a shear stress that on that front face is pointed downward with a torque that's going around counterclockwise like that. On the other hand, if I were to grab a little chunk of material from the right side, also make it in kind of 3D perspective because this is from a 3D shaft, let's draw that one enlarged. What will happen with this one is the shear stress on that front face is going to act in the direction of my little arrow that I drew. It's going to act upward. Do you remember equilibrium a little bit with shear stress? If you have the stress pointing downward on the front face, there would be this hidden back face. Let me kind of draw it with some dashed lines. Hidden back face that has to have an equal and opposite force on it, right? Force comes when you take this shear stress and you integrate it over the area or add it up, sum it up. You'd end up with an overall net downward force on the front face. It's got to be countered by an upward force somewhere else. So we assume that's on the back face. Same thing with this purple one. If it's upward on the front face, you will need another one that is downward on the back face. But there's a problem if we only draw those two loads on there. That is that this would create a net tendency of this little cube to rotate about an axis because you've got downward and upward. They're going to create a couple moments. This is going to start rotating. This has upward and downward. Same problem. It's going to start rotating. So you end up with actually an induced stress that is not on this front face here that I cut open. It actually acts down the length of the shaft. The direction of it we just figure out by putting these together tail to tail and head to head, one on the top and one on the bottom to create a moment in the opposite direction. So these two on the front and back are going to tend to cause rotation that way. The top and bottom ones will exactly cancel it out the other way. With the purple one, we end up with the same idea. You'd end up with equal and opposite stresses on the top and bottom, pointed head to head and tail to tail, head to head and tail to tail, so that these front and back ones would tend to cause rotation that way. The top and bottom ones tend to cause rotation the other way, so they cancel out. And you will actually see if you have a shaft made out of something like wood that maybe has a grain along here, when you twist it, you will sometimes get cracking and splitting down the length of the shaft. And that's actually caused by the shear stress that ends up happening not on that cut open circular face, but in the longitudinal direction because of the fact that these little cubes have to be in equilibrium. That's what these pictures are trying to show in part. If I come right here and I zoom in, I'm going to get a little cube that's going to have a stress on the front face that matches that direction, and then an induced stress on the top and bottom faces so that this cube will be in equilibrium, and that's the picture I drew right here. So not only does it change direction as you go around, it turns out the stress is going to have to be 0 in the middle, and it will increase linearly as we go outward. The stress needs to vary linearly with radial position, meaning it's going to be 0 at the middle, and it will be max at the outer edge. The 0 at the middle should make sense, because since the stress like on this side is going down, on this side is going up, as we move toward each other in the middle, you'd have a big problem if you had a non-zero stress right here and you had to have it acting both down and up at the same location. So they've got to decrease towards 0 at the middle, otherwise we have a big discontinuity there. We're going to assume that it varies linearly, 0 at the middle, max at the outer edge, and let's see what kind of equations we would come up with. If the stress varies linearly, that means that tau is equal to some times tau max. It's got to vary linearly with something, and we want it to vary linearly with radial position. Our book is going to use the Greek letter rho for radial position, and let's just scale it by a value c. Let me explain to you what these guys are, because this is not intuitive. This rho is what we call radial position. It's a variable that goes from 0 at the middle to r, or r0, to the outer radius at the outer radius. Okay, it goes from 0 to r0. I'll draw a picture in just a second to go with it. The thing I want to point out to you is that this guy is not density. I know a lot of places you use rho for density. In this equation, this is not density at all. This is radial position. It has units of length. And then what C is C is the max radial value, or in this case, it would be R0, the outer radius. So let me draw a picture of this. Let's say I have a round circle of a shaft. It's got an outer radius, R0. So that's going to be C. If I come out just part way along the radius, this would be rho. So if I wanted to figure out how the stress distribution looks, I already said it's going to be linear, 0 at the middle. So let's try at rho equals 0. We are at the center of the circle, and tau equals 0 over c times tau max. Tau is 0. Let's try at rho equals, I don't know, halfway out, r0 over 2. Well, then tau would be r0 over 2 divided by c times tau max. But remember, c, that's your biggest value that rho can possibly have. C is equal to r0. Let's replace c with r0. What we get is tau max over 2. And if we go out to the very outer edge, when rho is equal to the outer radius, tau would be r0 over c times tau max, but c is equal to r0, so we get tau is equal to tau max at radial location of the outer radius. So that's what this equation means right here. This is partially useful. It tells us what kind of stress distribution we expect at different radial locations. But I want to actually relate this tau max to the actual applied torque. So remember, these stresses are basically like you start with a big torque, and we're going to break that torque up into little bits of stress all around here, which when all summed up have to give you the torque. Well, how do we sum things? We take an integral. So torque is going to be the integral over that entire area of what? Torque is a moment. You get a moment by taking force times distance. So if I'm adding up a little stress times a little area it acts over, and I need to multiply it by its distance from the middle, well, that's its radial position, which is rho. The magnitude of the force is going to be the stress times dA. So rho is the distance of that point from the center, and this is the force acting on the little area. We did something similar for axial loading. With axial loading, our stress was completely uniform over the whole area. And if we wanted to find the total force, it's simply the stress times dA integrated over that entire area. Because the stress was uniform, we ended up with sigma times area, and we got that stress was just force over area. We're doing the same thing here. We want to relate the overall total summed up torque that you get by adding up all the stresses, but it's much more complicated because torque is not force. We need to take force times distance. So for every little point here that we're going to add up, their distance is going to be different. So I need to multiply by that radial distance. And then I need to also multiply by the force, which is going to change magnitude as we move out. It's also going to change direction as we move around. So my torque is going to be integral of rho. Now let's replace shear stress with what we said it's equal to. Shear stress comes from this equation, rho over c times tau max. So let me plug that in. Rho over c times tau max dA, right? I just replaced the tau with what it's equal to. Well, we can simplify this. Here's what's nice. Tau max actually doesn't change with position. It's just a single number. We're trying to solve for it. So we can pull that out in front of the integral. You know what else doesn't change? C. That's the outer radius of the shaft. Doesn't matter where you are on the shaft, the outer radius is still the same. So let's pull that out in front of the integral as well. So what's left inside the integral is the integral of rho squared dA. You might remember this from back in statics when you did things like the integral of x squared dA and the integral of y squared dA. This is an area moment of inertia. We are going to use the letter J for it because this is not the moment of inertia at the x-axis or the y-axis. This guy is called the polar moment of inertia. And you may have seen it before as an integral of r squared dA. Rho is just r, but it's not like a specific fixed r. It's a radial coordinate that changes as you move your way out. If you take this and you integrate over a circle, what you get is the polar moment of inertia. And here's the great news. We don't have to do this integral ever in this class. We can just look up J in the back of the book. All we need is J for a circle. J is pi over 2 radius to the fourth, or if you prefer, is pi over 32 diameter to the fourth. I recommend using pi over 2 r to the fourth. And the only thing you could make it more complicated is if it's a circle with a hole. It's not that much more complicated. J would be pi over 2 times the outer radius to the fourth minus pi over 2 times the inner radius to the fourth. And what you're doing is the polar moment of inertia of a big circle, which is this, minus polar moment of inertia of a little circle, which is that. Plugging that in, we get that our torque is equal to tau max over c times J. You can write it that way. We don't usually, though. We usually know torque and want to know shear stress. So let's rearrange it. Tau max is Tc over J. So if I want to find the max shear stress in a shaft, all I need is T, the internal torque right there. I need C, which is the outer radius. And then I need to be able to calculate polar moment of inertia. The other way you might see this is tau is T rho over J. So this would be same exact equation, but instead of finding the max stress, if I want to find the stress somewhere else in my circular shaft, not at the max location, I can plug in instead of C, rho, where rho is just the radial location. So if the outer radius is a 1/2 inch and you want to find the tau max, you plug in a 1/2 inch. If you have the same shaft, but you want to find the stress a 1/4 inch out, you plug in a 1/4 inch. Let's talk units for just a second. Torque, you know, has units like newtons times meters, or pounds times feet, or pounds times inches. C or rho, they've got units like meters. And what should J have? Ooh, what should J have? It's got pi over 2 r to the fourth. Remember how moments of inertia have units like meters to the fourth? So let's see. Tau is going to have units of a torque, there's a newton meter, times a radius, that's in a meter, divided by meters to the fourth. Guess what that simplifies to? Newtons per square meter, or pascals. So our units are good. If you ever solve for the shear stress in a torsion shaft and you don't get newtons per square meter or psi, you have made a mistake in what you plugged in. That's enough theory. 2 examples to finish out this video. So first example, we've got a shaft that is fixed on this end. It's got a 4 kilonewton meter torque that way, Farther down, it's got a 10 kilonewton meter torque. The other way, we have a radius of 75 millimeters. It's going to ask us to find the shear stress at point B, which is on the outer radius, and it's in between these two torques. And then they also want us to find the stress at point A, which is back here behind the 10 kilonewton meter torque, and it's not at the outer edge, it is 50 millimeters out. They also want us to draw it on a little box. The textbook probably called this a differential element, or they'll sometimes call it a material element. I prefer to call it a little box because that's what it looks like, as a little box. So let's do tau B first. For tau B, the equation is going to be T C or T rho over J. So I'm going to need to get the radial location. Oh, I know that. It's 75 millimeters out. I can calculate J using that. But T is the internal torque. I need the internal torque. So let's start with a free body diagram. Cut at B. So here's my cut edge. Applied to it is a 4 kilonewton meter torque that way. So internally, we're going to have the torque at B will need to be, if you sum torques, it'll be exactly 4 kilonewton meters. And practicing signs for torque, can you see this right hand rule? Your thumb would be pointed that way. So this is a positive internal torque. We don't really need that for today, but we will for the next couple classes when we start doing angle of twist problems. But for today, just remind you, this would be a positive internal torque. In fact, both of these are positive because your thumb is pointing outward on this end to get that torque and it's pointed outward on that end to get that torque. Okay, we have the torque. So let's see if we can get the stress. To do that, I'm going to need J. So I may as well just calculate it once. J is pi over 2 radius to the 4th. What was the radius? 75 millimeters. So 0.75 meters raised to the 4th power gives me 49.7 times 10 to the minus 6 meters to the 4th. So we'll use that and we get tau B is 4 kilonewton meters. Rho is the radial location of point B, which will be 75 millimeters out from the middle of the circle, 0.75 meters. J is 49.7 times 10 to the minus 6 meters to the 4th. And simplifying that, I get 6.04 times 10 to the 3rd kilonewtons per square meter, which is also a kilopascal. So that would be 6.04. If I get rid of the 10 to the 3rd, this becomes a megapascal, or 6.04 times 10 to the 6th pascals. Oh, those are right. This is probably the best way to give your answer, but they're all right. Now we need to draw this on a little cube. To do these cubes, I like to start by trying to draw the cube in a similar perspective to the way the original picture is. So hopefully that kind of works. I want these edges to kind of be parallel to my x-axis and this face to kind of match the perspective of that face. So now this is for point B. I need to figure out which sides of this to draw arrows on. And here's the challenge. With the way I drew this free body diagram, this torque is actually on the back face. So the cut we have looks like this, and our torque is in that direction. Think of it with your thumb coming out that way for your right hand. The other side of the cut would have been the visible face. And if you drew the torque on that face, it's got to be exactly equal and opposite. Also thumb coming out that way. So this is the one where I actually like to kind of draw those little arrows. That torque right there is being replaced by a bunch of little arrows like this. And point B, where was point B? Point B was right on the top. Point B is right up here on the top. So can you see that if I'm looking at the visible face, the little arrow at point B is pointing this direction. So the visible face over here that matches the visible face right there is going to end up with a shear stress in that direction. That's the one you get from looking at the matching face on the diagram. So on the back face, you should have a stress in the opposite direction. That would not be in equilibrium. That would start rotating. So I have to also draw the induced stresses on the other two faces like that. And that's what the stress on the little cube would look like. I find to do these, drawing the other diagram with the front face showing is the only way to get these right usually. If you want to turn it so you're actually looking at the front face, you can. your torque is that way. So at the top, your shear stress is going to the left. If you're at the bottom, your shear stress would go to the right. Over here, it's down. Over there, it's up. So then when we go to draw it on our little cube, that front face is this. And so this is the face we see that's perpendicular to my x-axis. So that is where we draw that stress. Let's do another one. We're supposed to do tau A. To do tau A, I first need to do a cut at A. So doing that cut, I'm actually going to draw both sides of the cut this time because I know I'm going to need them later anyway. So there's one side of the cut. There's the other side of the cut. What we have acting on here is a 4 kilonewton meter torque right there, 10 kilonewton meter torque right there. Then we're going to have the torque at A. Let me draw it as a positive torque, and we'll see if it comes out positive or negative, which would mean it would act that way, torque at A on that side of the cut. Let's sum torques. Summing all of the torques has to be 0. Pick a sign convention like that, positive. We get 4 kilonewton meters minus 10 kilonewton meters minus TA equals 0. So the torque at A would come out to be negative 6 kilonewton meters. Means I drew it in the wrong direction, which I knew when I drew it. Since I got 10 going that way and 4 going that way, I figured it's going to actually act that way. But I get a negative 6 kilonewton meters. First, let's calculate the stress. So tau A is going to be that torque. Let's just do the magnitude of it, and then we'll get the direction from the picture. It's going to be 6 kilonewton meters. Radial position of point A. This one was not at the outer edge. Instead of going up 75 millimeters, we're just coming out toward the front 50 millimeters. 0.05 meters. And then the J is the same, 49.7 times 10 to the minus 6 meters to the fourth, and we get a magnitude. This comes out to be 6.04 megapascals once you simplify and switch your units. Exactly the same as the other one because the torque is exactly as much larger as the radius is smaller. So we get the exact same stress at point A as we do at point B. Now I need to draw it on a little cube. So to do that, what I want to do is redraw these pictures. This torque came out to be minus 6 kilonewton meters, which means it actually acts in the other direction. It actually acts this way, plus 6 kilonewton meters. And point A is out here on the front. So if you draw your little arrows, they're going to go around like that. And on that front face, on that front edge where A is, it's not all the way out on the edge, but it's going to be acting pointing upward. I need to draw one of those little cubes, and it should have a similar perspective. There's my cube that's trying to be the same perspective as my picture. This face right here is the front face that matches this face right here. So that is the face where you want to draw your little upward arrow. So there is where tau A is going to act. That is the important one. The others are found by equilibrium. So on the back face, we go down, and then it would be on the top face and the bottom face. We end up with induced stresses. Let's do one more example. We have this shaft. It's got 4 torques acting on it. They are all given right here. We are told that the shaft section between B and C is hollow. There are the dimensions. We are supposed to find tau max and tau min in section BC. To do that, let me first draw a little sketch. Since it's hollow, the shear stress is going to have that kind of a behavior. It's going to be tau max is at the outer radius, and tau min is going to be at the inner radius. There's no stress in the hole in the middle. Then we also are going to want to do a free body diagram cut between B and C. So let's take that cut. I already drew a little purple dashed line where I want to take the cut. You can keep everything to the left or the right. I decided to keep everything to the left. So we keep 2 of the wheels, and then here is our cut. On our free body diagram, we'll end up with a torque of 6 kilonewton meters acting on wheel A, and a torque of 14 kilonewton meters acting on B. And then the torque at BC, let's use our positive sign convention, which would be thumb coming out. That would be our torque in section BC. It's a positive torque, thumb coming out and away from the shaft. If you sum those torques, you will find out it's actually negative. It should be minus 20 kilonewton meters. I drew it in the wrong direction is what the negative means. It's actually a negative internal torque. But let's find the magnitude of the shear stress. To do that, we're going to need J. So J will be pi over 2 times the outer radius to the fourth minus pi over 2 times the inner radius to the fourth. That comes out to be pi over 2 times The outer diameter is 120. That means the outer radius is 60 millimeters, so 0.06 meters to the fourth minus pi over 2. Inner radius, well, inner diameter is 90. Inner radius is 45, so 0.045 meters to the fourth. That number is 13.92 times 10 to the minus 6 meters to the fourth. So we can find the stresses now. Tau max, at least the absolute value of it, is going to be 20 kilonewton meters. That's the torque, times the outer radius location, 0.06 meters, all over J, 13.92 times 10 to the minus 6 meters to the fourth. Multiplying that out, I get 86.2 times 10 to the third kilonewtons per square meter, which is 86.2 megapascals. That's how big the max shear stress will be, and the min shear stress. Well, same torque, 20 kilonewton meters. Only thing that changes is now we are at 0.045 meters, 45 millimeters out. Same J, 13.92 times 10 to the minus 6 meters to the fourth. And this one is going to be 64.7 times 10 to the third kilonewtons per square meter, or 64.7 megapascals. Let's do one little extension. We dealt with shaft BC. Now we're going to look at shafts AB and CD. We're going to be told, let's make AB and CD solid and find the minimum required diameter given an allowable shear stress. Shafts AB and CD are solid. Find the required diameter if the allowable shear stress is 65 megapascals. The equation I'm going to use is tau is T rho over J. I got to solve for diameter in there somehow, so I'm going to need to write J in terms of diameter, rho in terms of diameter, and I need to find internal torque. So let's cut at AB. So cut between A and B, draw a free body diagram. That's just this little bit, cutting in between there. We only have the one wheel on there. Cutting right here and just keeping everything to one side or the other. So the torque on this one is TA, which is 6 kilonewton meters. So the internal torque in section AB is actually going to be minus 6 kilonewton meters using our sign convention. Let's do the cut at CD as well. Cut at CD is right here, and I'm going to keep the easy side, which is just this right here. So CD, I've got the one wheel on the end and then this shaft, and then I cut it right there. So what's applied here is we had a 6 kilonewton meter torque applied in that direction. Our internal torque in CD, if it's positive, that would mean our thumb is coming out that way. This one actually comes out to be plus 6 kilonewton meters. So one of them comes out to be a positive torque, the other one comes out to be a negative torque, but the point is they have the same torque magnitudes, they'll both need the same required diameter. They told us the max tau allow is 65 megapascal, so let's put that on the left side of our equation. 65 times 10 to the 6th newtons per square meter equals our torque magnitude, which for both of them is 6 kilonewton meters. And then I need rho is my radius. Let's just solve for radius and then get diameter afterward. Rho is going to be my outer radius that I don't know. And J is going to be pi over 2 times radius to the fourth. And if I solve for radius, I can just double it and get the required diameter. Let's just convert units here. Kilonewtons, I'll need 1,000 newtons per 1 kilonewton to cancel kilonewtons so that I have newtons on both sides of the equation and solve for R. Intermediate step is R cubed needs to be 58.8 times 10 to the minus 6 meters cubed. You end up with meters cubed because the newtons cancel on both sides of the equation. We have meters squared. That when I bring it up over here with this other meter gives me meters cubed. That's good because R cubed is in meters cubed. So that means that R will be in meters, 38.9 times 10 to the minus third meters to be precise, which is 38.9 millimeters. Doubling that, the diameter is 77.8 millimeters. And that solves that problem. The hardest part of torsion shear stress problems is these little pictures. We're going to practice them a little bit now. We're going to practice them a bunch at the end of the semester after we've learned several other kinds of stresses. And that is stress in torsional shafts.